In 1984, after Helita introduced the first early streamer emission lightning conductor on the market, Helita started working in collaboration with the Laboratoire de Physique des Décharges, the discharge physics laboratory, team number 114 of the French CNRS. This project led to the filing of a joint CNRS-Helita patent for the pulsar. Helita also asked the Discharge Physics Laboratory to develop a test procedure to evaluate this lightning conductor in comparison with other conventional systems. You're now going to attend a test session on a pulsar. The pulsar is an early streamer emission lightning conductor manufactured by Helita. The pulsar has a self-contained device which sends high-voltage pulses to the point of the lightning conductor at controlled frequency and amplitude. These tests are designed to evaluate the advantage of the pulsar over a Franklin point of the same geometry and placed in the same conditions. A large spark represents an electrical discharge which leads to the breakdown in atmospheric air. From a purely qualitative standpoint, we can say that a very close similarity exists between the development phases of the electrical discharge in air and the natural ascending discharge. From the quantitative standpoint, however, a scale factor with a known ratio applies, requiring the transposition of the laboratory results to natural conditions. The analysis of a negative lightning stroke reveals 4 different phases. The effectiveness of a lightning conductor depends primarily on its ability to develop an upward leader as early as possible. To simulate the electrical field conditions prevailing in a storm as accurately as possible in the laboratory, it's necessary to superimpose a permanent field which corresponds to the field due to the charge distribution in the cloud, typically 10 to 20 kilovolts per meter, and an impulse field, the rising front of which lasts several hundred microseconds, and which represents the field induced by the downward leader approaching the ground. As the downward leader approaches the ground, the electrical field at the lightning conductor rises extremely rapidly. Unfortunately, it's impossible to generate these waveforms in the laboratory. So a Marx generator is employed to deliver bi-exponential waves, whose values are caused to coincide at 2 points of interest, such as 1 kilovolt per centimeter and 5 kilovolts per centimeter, which represents the zone of interest for ionization. In the experimental procedure, a Franklin rod is compared with an early streamer emission lightning conductor. The Franklin rod is first placed in the interval. A series of shocks are applied to it. The probability of breakdown is determined and the time of breakdown is measured. In the second step, by maintaining the same geometric and electrical field conditions, the same tests are performed on the active system. We can then compare the data obtained from the time of breakdown and the probability of breakdown. This evaluation procedure is a comparative statistical analysis of two series of 100 shocks in which the breakdown conditions are measured. 100 shocks are first generated on the early streamer emission lightning conductor in a Franklin rod configuration. The same 100 shock test is then performed on the early streamer emission lightning conductor in an actual configuration. The electrodes are separated by a distance of several meters. The variations in the discharge current, in the light emitted, and the climatic parameters are recorded for subsequent physical analysis. We can see right away that the number of breakdowns obtained with the pulsar is greater than the number observed on the Franklin rod. The pulsar also displays a breakdown advance of a few hundred microseconds. In natural conditions, it can be estimated that the pulsar system will be more effective than the Franklin rod because it will capture the lightning earlier and more often. Helita maintains its position as the world leader in early streamer emission lightning conductors, partly because of the quality of its products. Helita is the only company that conducts systematic production tests on its manufactured products. It performs these tests in the high-voltage laboratory of Bagnères de Bigorre. If the lightning strikes the point of the lightning conductor, the external air gap becomes conductive, and the current flows to the ground along the metal body. The tests performed at Bagnères, including voltage and current tests, are intended to check that this effectively occurs. The electronics is tested to check that its internal insulation voltage is higher than the breakdown voltage of the external air gap of the lightning conductor. This means confirming that the lightning shock is transmitted to the ground without destroying the electronics. This test is performed with a voltage of 30,000 volts. If a batch contains a defective part, it's accordingly destroyed. All the electronics of pulsar systems are tested by this method. The final production test is performed on the finished pulsar. This test helps to confirm the transmission of the lightning current to the ground. Current shocks of 10,000 amperes are used for the purpose. The pulsar tested is then inspected with the pulsar testing unit before sale.